Okay, let's move on to talking about independent events. Now, the way that the word independent and mutually exclusive sounds in the English language um, would make it seem as though uh, they're the same thing. Because what is it that we usually think of when we think of, you know, things that are independent? We think that they stand alone, right? If two people are independent of each other, you tend to think of person one standing on their own 2 feet, completely separate from, not depending on person number two, who's independent from person number one. So we tend to think of independence like a Venn diagram like this. The sample space would be the world. We're all living on Earth. And we've got person A and we have person C, each with their own, beliefs and personality, and they're completely independent of each other. So this idea of how we define independence actually runs afoul of how we talk about the independence of events when it comes to probability. So this is an example of where your common sense, your personal experience is going to interfere with understanding the concept of independence, but defined in mathematical probability. Okay. So keep that in mind. These mutually exclusive disjoint events and independent events are two different things. And in fact, you cannot have two events being independent unless they are not disjoint. All right, so that's explaining a lot. Let me show, okay, what I'm talking about. So here we are with the definition of independent events. So if two events A and C are independent, then any one of these three conditions will be true. Any one of these three conditions will be true. Sometimes it's easier to show that two events are independent by looking at, maybe this condition. That might be easier to demonstrate that two events are independent rather than this one. Okay, so that's why there's three. But these three different forms demonstrate the same idea that two events are independent. So, first of all, like what does the first one say? It says that if A and C are independent, then the probability of A will be equal to the probability of A given that C occurs first. Then we look at this last one. The probability of A intersect C will be equal to the probability of A times the probability of C. And I'll give some examples of both of these here in a minute. So again, note that when two events are independent, then 1, 2, and 3 above are all true. Therefore, when one is presented with two events, and it is unknown whether they are independent or not, 1, 2, and 3 above can be used to test if two events are independent of each other. So let's look at this testing to determine if two events are independent. So for example, I've got three Venn diagrams here, right? 1, 2, and 3. But only one of them is a Venn diagram where events A and C are independent. So you can look at the three of these and functionally, superficially, they all look the same. Because what do you notice? A and C in all three Venn diagrams, they're all non-disjoint. They are non-mutually exclusive. They all overlap. And all of them have, something in their intersection, right? The first one has a three, the second one has a two and a three, and the third one has a one, two, and a three. There are some, subtle differences between them, but you don't know which of these subtle differences are actually meaningful. Okay. Um, so what we want to do is we want to now apply any one of these three properties of events, two events being independent. We want to apply any one of those three to these three Venn diagrams and use it as a litmus test to determine mathematically whether two events are independent or not. So, so let's move on to actually doing that. And what we're going to use to test for independence, we're going to use the third uh, equation, and that's where the probability of the intersection is equal to the probability of the first event times the probability of the second event. So here across the top, I've got the same three Venn diagrams that we saw on the previous page, with all the same attributes of all three. But what we're going to do is we're now going to apply this test of independence to all three scenarios, all three Venn diagrams. So how is it we're going to do that? Well, notice that we have an expression here on the left, and we have an expression here on the right. And we need to determine whether when we calculate this and calculate that, we want to know whether they're equal or not. That's why I've got that little question mark over the equal sign. Are those two expressions on the left-hand side and the right-hand side, are they equal to each other? If they are equal to each other, then the two events are independent. If they're not equal to each other, they're not independent. They are therefore dependent. So let's look at this. So in order to calculate the probability of A intersect C, okay, the probability of A intersect C is going to be the order of the intersection divided by the order of the sample space. And let's go ahead and carry that down. So the order of the intersection, there's only one. Then the order of the sample space is 6. Now, on the right-hand side of the equation, we have this expression, which is going to be the order of A over the order of the sample space, the order of C over the order of the sample space. And I already wrote down the order of A, meaning the number of outcomes in A is 3, right? And so for the order of A here, I've got 3. The order of C, you can look up above, is 4. So we have 3 over 6 times 4 over 6. And when we simplify what we've got on the left, so on the left-hand side, we've got 1/6. And if I simplify what I have on the right, this simplifies down to 2/6. So clearly you can see that 1/6 is not equal to 2/6. Those are two different values, right? Two different fractions. It's like if you've got one slice of a 6-sided pizza, that's not the same as 2 slices of a 6-piece pizza, right? And so because this expression on the left is not equal to the expression on the right, A and C are not independent. A and C are in fact dependent on each other. All right, let's look at this second Venn diagram. So again, we're applying the same test of independence. The intersection, the order of the intersection of A and C is going to be 2 over 6, because what's the order of the intersection? There's 2. And then the expression on the right is we're going to have 3 over 6 times 4 over 6. And when you simplify both sides, the left-hand side will just keep at 2 out of 6. And on the right-hand side, that'll simplify down to also 2 out of 6. What's on the left does equal what's on the right. So therefore, A and C pass the test of independence, and they are independent events. And if we apply the same process to this third Venn diagram, again, you'll see a similar condition to what we had in the first, which shows that events A and C, defined as they are here up above, they are dependent on each other. So at first glance, you couldn't really tell whether these two events were dependent or not. You had to apply this test and do the math to determine whether the two events were independent or dependent. Now, let me share a little bit more. I'm actually going to take what is on the next page and just kind of put it on this page, again, to maybe show the same thing in a different light instead of starting over on a different page. So let's look at Venn diagram 1. And so if we calculate the probability of A by itself, right, we already figured that out to be 3 over 6, which is 1/2. Now, I hate it that word shifts everything up. I'm sorry. Let me try and rewrite this to where it doesn't do that. So the probability of A, there we go, equals 3/6, which is equal to 1/2. Okay, now let's look at the probability of A given that C occurs first. Okay, now, if C occurs first, this is conditional probability, which means that our sample space shrinks down to event C, event C. So this is going to give us the probability of A occurring given that C occurs first is going to be 1 out of 4. We have 1 out of 4. Now these two probabilities are not equal. And this is one of the tests. I think this was the first test of independence on the previous page. But think about what this says, is that event C changed the probability of event A occurring, right? If event C occurs first, it actually reduces the probability of A occurring. That sounds like a dependence to me. And we know that this is a drop in the probability of A because we calculated the probability of A occurring all by itself. It's 1/2. So if we think about this in terms of maybe two people, okay, and if we have one person standing in a room by themselves and they appear to be happy and not affected by anything in their environment, then we can kind of take that reading of that person by themselves. But let's say a second person walks into the room, and right away you see that the disposition, the demeanor of the first person changes, and that second person comes into the room. Then you would say that the that the second person coming into the room affected the first person who was already there. That's kind of what we got going on here. By themselves, or by event A by itself, it has a probability of 1/2 occurring. When event C comes in, it lowers the probability of A occurring. It has an effect on A. So therefore, A and C are dependent on each other. One affects the other. Now let's come back over here to Venn diagram number 2. So what's the probability of A occurring? Well, we figured that out to be 3 out of 6, okay, which is 1/2. And what's the probability of A occurring given C occurs first? Well, let's see. The outcomes of A that are in C, there's 2 of them. And then how many do we have in C altogether? We've got 4. So a probability of 2 out of 4 is 1/2. Well, these are equal. So what this says is that event C did not change the probability of event A occurring. Okay, so because event C happened first and didn't change the probability of event A occurring, A and C are independent. So think back to this example I gave of people. So if person A is in the room all by themselves and they're happy-go-lucky and don't have a care in the world, and person C walks into the room and person A still remains happy-go-lucky and without a care in the world, then that second person coming to the room had no effect on person A who was already there. Person A is completely independent of person C walking into the room. So they had no influence, they had no effect on the person that was already there. So likewise with events A and C, C had no effect on the probability of A occurring. So A and C are independent. So this is just using this first test. Sorry about that. Of using the first test, which I think was if the probability of A equals the probability of A given that C occurs first. Okay, so I just kind of applied that different test. But notice whether I used, this first test or the third one, we still got the same assessment that they're independent here and they're dependent there. So I thought it was important to maybe put these on top of each other here so that you could contrast the similarities and the differences. I kind of use this other test here on the next page, and you can kind of follow that yourself and see the results that I came to. Okay. But I'll leave that up to you to do. But just know that that's there for you. And let me add one more thing. And that's to remember that mutually exclusive or disjoint events can never be independent. So again, what does that look like? So here's our sample space with 2 events, A and C, right? A and C are disjoint. So why are disjoint events never independent? Look at them. They're separate from each other. Okay. But let me put it to you this way. Um, if if an outcome, I'm going to label this X, is in event C. So an outcome is an event C. It automatically excludes the probability of the outcome um, appearing in event A. So, C is directly affecting whether A occurs. So if you have disjoint events, they can never be independent because if something occurs in one event, it automatically excludes it from happening in the other. So if you want to have any chance of showing that two events are independent of each other, you can, if this is the case, you can right away say, oh, they're dependent. But if there is an intersection between two events, if the order of the intersection is not zero, then you have to apply this test of independence to determine whether the two events are independent or dependent. Okay. I think that concludes this definition of independence and testing for independence. Let me know if you have any questions.